Hello everyone, Dr. Chen here. So let's discuss elastic potential energy in this lecture video and energy conservation involving elastic potential energy. Elastic potential energy, we can also call it a spring potential energy. Now, unlike gravitational potential energy, the gravitational force for object on the surface of Earth is almost a constant. Weight is almost constant, and spring force is changing, depends on what's the deformation of the spring. So let's first try to understand what is the work done by the spring force. So more generally, we have just learned if the force and the displacement is in the same direction, force times displacement will give us work done by the force. So if we have constant force, and the displacement is delta x, the constant force is almost fx, then the work done by the force is fx delta x. Fx would be this side for the rectangle, and the delta x is the short side for the rectangle. So for constant force with displacement, constant force Fx with displacement delta x, this area of this rectangle will give us the work done by this constant force over this displacement. Now, if we don't have a constant force, we have a force that is changing over time, we can approximate the work done by this force by cutting this into a lot of segments, basically a lot of small rectangles, and the force here is approximately a constant force. So constant force times displacement, constant force times displacement gives us the work done by each small short displacement. And if we add everything together, it gives us the work done by this force, which is a force changing over the position. Now, the individual rectangle gives us the work done in this displacement. So from initial position to final position, we add the area of all the rectangle together. We get this one, which is work done in the first rectangle, work done in the second rectangle, and so on. So which also gives us the area under the curve exactly equal the work done by the force particle during displacement from position xi to xf. So if we plot the force on the y-axis and the position in the x-axis, then we have a curve for the force versus position, and this area under this curve give us the work done by this varying force. In conclusion, the work done by a changing force on an object for displacement equals to the area under the graph force versus position. Okay, now we're ready to find out what's the work done for a spring force. So suppose initially a block attached to a spring, initially at a position 0, the deformation of the spring is 0, which means the spring is in the equilibrium position in the beginning, and then we apply force to pull the block from here to here. What would be the force we apply as a function of the position of the block? Hooke's law tells us the spring force is given by negative kx x is the position of the block. So the force versus position is linear. And now we also learned area under this curve divides the work done. So what will be the area of this rectangle? We know this is x. We know this force is kx. The magnitude is kx. Now the force we applied is in the same direction of displacement. Spring force is in the opposite direction of the displacement. This is spring force in the opposite direction of displacement. The force we applied is in the same direction as displacement. So we want to calculate the area of a rectangle in a triangle AB. So area of this triangle should be 1/2 A times B. So the area should be 1/2 kx times, this is one side, x, so it's 1/2 kx squared. And this is exactly the work we need to do to pull the block from 0 to x. So the work done by the force we apply is 1/2 kx squared max. And this is also the elastic potential energy stored in the spring when the spring goes from 0 to x. So if at the beginning the spring is at the equilibrium position, the potential energy of the spring in this case, of course, is 0. Now if we press the object by a displacement of x, the potential energy of the spring in this case is 1/2 kx squared. Starting from 0, if this is equilibrium position, and here we press the spring by deformation x, and what we do from B to C is we release our hand, the object will spin, the spring will push the object out, and what would be the velocity of the block after the spring ejected out? So all the potential energy of the spring is going to be transformed into kinetic energy of the block. So the kinetic of the block should be equals to 1/2 kx squared we have there, and it's also given by 1/2 mv squared. So if we know kx, we know m, we can calculate what would be the velocity of this object. This is the example shown on the textbook. So to summarize, if we have a spring, then the potential energy of the spring is given by 1/2 kx squared. And we can check the SI unit is for 1/2 kx squared would be exactly equals to kilogram meter squared second squared. So equals to joule. And for mechanical energy conservation, we should also have kinetic energy plus potential energy equals kinetic energy plus potential energy. So initial potential energy plus potential energy equals final kinetic energy plus potential energy. Now the difference is this time for potential energy we have two different kinds of potential energy now. We have gravitational potential energy and elastic potential energy. We have gravitational potential and elastic potential energy. So if there are both gravitational force and the spring force, we need to use this equation for energy conservation. So if there is only gravitational force, then we just need to include gravitational potential energy in the problem. If there is only spring force, we only need to include elastic potential energy in the problem, also called spring potential energy. The elastic potential energy of a stretched or compressed spring is always positive. Is this right? Is it? So elastic potential energy is given by 1/2 kx squared. K is always positive. X squared, a stretched or compressed spring, it has deformation, so S is not 0. So this is x squared is always positive. K always positive. So potential energy always positive, which is right. If we launch the object with initial elastic potential energy 1/2 kx squared, and eventually for the final state, the spring potential energy will be 0, or the spring potential will be transformed into kinetic energy. Let's do one example. So we have a block whose mass is 0.2 kilogram. There's no friction because we use air trap. The spring constant is 5 Newton per meter. We pull on the box, stretch the spring to 0.1 meter and release from rest. And then the glass moves back. We want to find out what will be the velocity of the block here. So what are the forces acting on the block? Of course, we have gravity. Let's use mg to eliminate confusion with work. Mg, the force. And then we have normal force. And then we have spring force. Okay. And displacement is in the horizontal direction. So which force does work? We need to find out what's the angle between the force and the displacement. So we say the displacement is in this direction. Mg, normal force. So the angle between mg and the displacement is 90 degrees. So mg doesn't do work. The angle between normal force and the displacement is also 90 degrees. Doesn't do any work. And the only force doing work is spring force, because spring force is in the horizontal direction. So the only force that work is spring force. So mechanical energy conserved. So we write down the mechanical energy conservation equation. KEI plus PEI. Now we only have spring potential energy in this question. KEF plus PEF. KEI is 0. PI is 1/2 K xi squared. KI something we want to KF something we want to solve VF, and the PI 1/2 K XF. XF is 8 centimeter. So plugging all the numbers, 1/2 times 5 and 1 square equals 1/2 times 2.2 VF square plus 1/2 times 5.08 square. Now to solve this equation, we'll find that the final velocity is 0.3 meter per second. Now this problem we used the principle of conservation of mechanical energy. Now we also need to check, is mechanical energy conserved in this problem? Now we check the only force that work is inelastic force, and normal force, gravitational force doesn't do any work, so mechanical energy is conserved. Only force that work is spring force, and spring force is a conservative force, so mechanical energy is conserved. And this is why we can use conservation of mechanical energy to solve this problem.